Okay, let's take a look at those graphs and see how everything is put together. And we're going to look at each individual functional group to give you a proper representation of what each one of these graphs looks like and what regions we have to pay attention the most. We're going to start with the alkanes. These are your typical carbon-carbon single bond molecules that contain potentially carbon-hydrogen bonds as well. All right, so what we do know based on the calculations that I talked about in the previous video is that carbon-hydrogen bonds are expected to appear around 3000 inverse centimeters in the graph, and the carbon-carbon single bonds are expected to appear around the 1200 region in the spectrum. And so let's take a look at the spectrum for pentane, which is 5 carbons, only carbon-carbon single bonds being present. All right, so this is a rather simplistic spectrum. Now, what we're really seeing here is not the absorption spectrum, but rather the transmittance spectrum, which means that we're looking at how much light has been passed through the actual cuvette that holds the sample. And notice that here the values go from 0 to 100, right? So if your sample has absorbed a lot of the light, the amount of it being transmitted is going to go down. So whenever you see these things reaching almost the x-axis, what that's telling you is that you're absorbing strongly a lot of light out of this thing. So think of this as being an absorption, even though we're looking at it from the point of view of transmittance, right? But that's an absorption, that's an absorption, that's an absorption, right? And this is pretty strong. This ones right here are like medium to strong in terms of their intensity. All right, now the key value to be on the lookout for is the 3000 inverse centimeters. That's where we expect to see the carbon-hydrogen bonds. And notice that the actual peak of absorption appears a little bit shy of the 3000 value. Because the other thing too that is important to mention, the values in the infrared spectrum increase from right to left, right? So we have 4000 inverse centimeters on the left side. We have 500 inverse centimeters on the right side. And the reason why is because this is set up as if you were doing your typical UV spectrum that is based on wavelength, right? So the wavelength and energy are inversely related, right? So this has the lowest wavelength, this has the highest wavelength. So it's technically addressed in terms of wavelength absorption, but we are expressing all of the values in terms of inverse centimeters, which is the wave number. So, I don't know if really this was necessary to do it this way, but this is the way that's been done for a long time and continues to be done this way, so we're going to stick with it. All right, so going to the left increases the number. So having all of these values to the right of the 3000 line means that we are below it, slightly below it. Not by a lot, but we are below it. Technically speaking, from within 2800 to close to 3000. Okay, and those represent what we call the carbon-hydrogen stretching frequency. So this is where your carbon-hydrogen bond is stretching back and forth, elongating and compressing, elongating and compressing. And your carbon-carbon stretching bonds are going to fall somewhere around the 1200 region. But then the thing is this: when you go below 1500, and I'll even extend it to about 1400. When you go below 1400, we're getting to what's called the fingerprint region. And this is the region that is unique to the molecule. This is the region that's actually used by spectroscopists to identify the exact molecule you're looking at. And physicists do this all the time when they're looking at light coming from outer space. They examine the infrared light in the fingerprint region, and they can tell you exactly what organic molecule or what inorganic molecule is present in outer space. But for us chemists, trying to memorize all the patterns for the specific molecules is not very helpful. So what we're going to focus instead on is the region outside of the fingerprint, the one that's more general, but that tells us with certainty that we have, one particular functional group present. All right, but for now, keep in mind that pentane contains sp3 carbons, and these bonds right here are sp3 carbon CH bonds, which fall below 3000, slightly below it. So let's take a look at the alkenes and see what happens with, this particular functional group. Now, based on the formula, we expect that carbon-carbon double bonds are going to fall roughly in the vicinity of 1600. And when we look at a graph, a representative graph, this is one pentene, so it's the same five-member carbon chain, but this contains a carbon-carbon double bond. All right, so what we see is a few things. First things first, notice that marking that 3000 limit, we still have peaks that fall below it because we still have sp3 carbons present in one pentene. But then we have a peak that appears above the 3000 mark, specifically at 3080. And what this represents is a carbon-hydrogen bond that is part of a sp2 hybridized carbon. So you actually push it a little bit further. And the reason why is because sp2 carbons have greater S character within them. And greater S character means that you see more nuclear charge, which means that your bond is going to be stronger. So the overall amount of energy required to stretch the bond now it's higher. Now you pay a higher price because of that hybridization. But the signal itself is rather sharp. In this case happens to be relatively strong. It's not the strongest one, but it is medium strong in terms of intensity. Notice too that around 1643 we have a relatively relatively strong peak that appears. This is your carbon-carbon double bond as predicted by the formula. And over here in the fingerprint region we have two relatively strong peaks that represent a bending mode. This is technically when the bonds right here kind of bend closer to each other and farther away from each other, so they make more acute and more obtuse angles. And in the case of a molecule like 1-pentene, we technically have 3 hydrogens bound to the alkene functionality. So we see these two bonds, these two stretching bending frequencies showing up in the fingerprint region. Okay, so here's the same graph, a little bit more elongated, so we see more clearly what's happening. Now what I'm going to do is I'm going to show you another alkene. This is 2-methyl-1-pentene, which only has 2 hydrogens present. And notice the fingerprint region. With the 3 hydrogens bound to that alkene, we had 2 peaks in the fingerprint region. But now with only 2 hydrogens, bound to the alkene in a geminal fashion, we only see this strong peak at 188 inverse centimeters. But the carbon-carbon double bond still shows up at 1651. Although if you look carefully, it's a little bit less intense, but roughly the same, around the mid 1600s. And you still have that peak above 3000 for your carbon-hydrogen bonds of sp2 hybridized carbons. Change the picture to a cis 2-pentene molecule that has this given configuration. So now the hydrogens are cis to each other, right next to each other in the carbon-carbon double bond fragment. And what you see now is a peak that falls at 698, so a little bit lower energy than we saw for the geminal case. The carbon-carbon double bond still falls in the mid 1600s, but notice how much weaker it is. It's not as strong as your geminal or even your terminal alkene that had 3 hydrogens, right? So now the intensity here is decreasing, but you still have that peak above 3000, right? Not by a lot, but it is above 3000, 3016 to be exact, representing the fact that you still have carbon-hydrogen bonds involving sp2 hybridized carbons. Now trans 2-pentene, looking at this particular setup in the fingerprint region, we see that strong peak at 965. So now the energy has gone up. You still have, technically speaking, a peak showing up in the mid 1600s for the carbon-carbon double bond, but notice how much weaker this is. Now the reason this is happening is because in this molecule there's a lot more symmetry than we saw in the cis configuration and even the geminal configuration or terminal configuration. So the more symmetrical your molecule becomes, the less intense this peak ends up being. We still see that peak at slightly above 3000, which represents the CH bond on a hybridized sp2 hybridized carbon, so that's still there. But getting on to an alkene that contains 4 alkyl groups bound to it and only 1 hydrogen, what you do see is also that that carbon-carbon double bond is still showing up with very weak intensity. And this has to do from the fact that now we're putting a lot more alkyl groups around it. This has become more symmetrical, a lot more symmetrical than it was before. The peak around the fingerprint region is showing up at 800. Right? It's showing us kind of like an intermediate case in terms of the intensity. And we still have that peak above 3000. It's a little bit hard to see here, but it's still showing up right there, 3035, meaning that we still have that carbon hydrogen bond bound to the alkene fragment. All right, so finally, we get to an alkene that doesn't have a CH bond, right? So we have alkyl, 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 and alkyl bound to the alkene fragment. And right here, what you do see is that there's no clear bending mode below 1000 inverse centimeters that you can attribute to this thing. And the reason why is because you have, come up with a very symmetrical molecule. And likewise, the carbon-carbon double bond in the mid 1600s, or in this case 1700, is very, very weak because this is as symmetrical as it gets. So another way to look at it is that the less carbon-hydrogen bonds that you have on that alkene fragment, the less intense your carbon-carbon double bond peak becomes. So sometimes in cases like this, it's a little bit hard to tell that you do have the carbon-carbon double bond. And here it's even worse because as a result of not having the carbon-hydrogen bond on the alkene fragment means that you don't see that peak above 3000, right? It's basically absent here. And this makes the assessment a little bit more difficult. So you have to be a little bit careful and you have to be on the lookout for this type of issues that may arise with the spectrum. All right, so the last thing I want to say in respect to the alkenes is that generally speaking, when you arrange them in this order, so you have only mono substitution on the alkene, you have disubstitution in the case of vinylidene, cis, and trans configurations, you have trisubstitution and tetrasubstitution, you see, generally speaking, an increase in that carbon-carbon double bond frequency. And the reason why is because you are dealing with stronger carbon-carbon double bonds. And this is the order that you would see from the general reactivity of alkenes, right? You saw that the monosubstituted alkenes are less stable than disubstituted alkenes. And within the disubstituted series, vinylidines tend to be a little less stable, then cis, then trans, and then finally you have your trisubstituted and tetrasubstituted alkenes being the most stable, right? So this kind of is a throwback to Zaitsev rules in terms of your alkene formation from dehydrohalogenation or similar reactions. So it's kind of nice to see that this is also represented in the infrared spectrum itself. All right, now all the values above 3000 once again represent the carbon-hydrogen bond, if you have any. The tetrasubstituted alkenes, of course, do not have carbon-hydrogen bonds on the alkene fragment, so you do not see that peak showing up above 3000. And also that peak in the infrared, the fingerprint region, is not really showing up. So just to give you a final look at this, you can think about the LUMOs and the HOMOs of the individual molecules. And here we have the trans configuration, over here is the cis configuration, and this is the geminal or vinylic configuration. If you draw the LUMO bond on one of the carbon-hydrogen bonds, and then compare it to the other carbon-hydrogen bond, right? So you have to have a HOMO interaction within the molecule that's interacting with the LUMO in that same molecule. And so what you see here is that in the trans configuration, there is a rather good overlap. You have the right type of angle. They're basically parallel to each other. So the HOMO of that bond is interacting relatively well with the LUMO of the other bond. In the cis configuration, however, the HOMO interacts very little with the LUMO because it's now interacting with the lowest electron regions of those particular orbitals. And when you look at the um, geminal configuration, there is some interaction, but it's kind of almost orthogonal. So the interaction is not the greatest. So the best one out of the three for sure is the trans configuration. And as a result of having the best overlap between the HOMO and the LUMO orbitals, you have the strongest carbon-carbon double bond in the series. So that's really, really interesting to see. All right, so ultimately, yes, you're going to have the stronger bond with your trans configuration, intermediate strength with the cis, and the weaker one with the geminal case. And so this is manifested in the infrared spectrum by having higher frequencies for the stronger interactions and lower frequencies for the weaker interactions. It's a great way of telling what's happening electronically with your molecules. Okay, so um, it might be helpful for you guys to also pay attention to the fingerprint region in order to make a distinction between whether you have the mono, the vinylidene, cis, and trans. And one thing that might help you to remember this is kind of the order, which also goes in line with whether you have a stronger bond or a weaker bond. Anyway, I'm going to stop the video right here, and in the next one we're going to talk about the triple bonds. So see you then.